Okay, continuing section 11.7, maximum and minimum values. We now arrive at a theorem which is basically the analog of the closed interval theorem from a closed interval test from Calc 1. This is now for three-dimensional situations, or a function f of two variables, x and y. Right? So what we'll discuss now is we'll talk about the value of the function f on a closed bounded set D. Remember that D is closed if its boundary if it contains all the points along its boundary, which this has been drawn so that we see that it's closed. It's not a dashed line, so it contains all the points in its boundary, and it's bounded because we can fit some circle of radius r or some disk of radius r around it and completely contain it. So closed bounded set D, and recall that we're interested in points x comma y in this closed bounded set because those are the points that we plug into the function f, and it gives us some real number output. So we're looking to maximize or minimize the function f on a closed and bounded set, and the way to do this is two steps. First, we find the values of f at the critical points of f in D. So we'll do exactly what we've already done in this section for that step. The second step will be to find the extreme values of f along the boundary of D. And this will be the new part of this technique when we work on the problem below. And then lastly, what we'll do is we'll compare the largest values and the smallest values on either of these lists, and whichever one is the absolute, the largest one of the entire list is the absolute maximum, the smallest one on the list is the absolute minimum on the closed bounded set D. So just like the closed interval test, only now we're dealing with a little slightly more complicated geometry. So the first example says, find the absolute maxima and absolute minima for the function on D, the triangular region with vertices 2, 0, 0, 2, and 0, negative 2. Okay, so looks like we have a closed set, it's a triangular region, including these vertices and the lines that connect them. And that's in the plane, of course, 3 points lying in the plane forming a triangle. So 2, 0, 0, 2, and 0, negative 2. Now the function is fairly simple. That's nice. So it'll keep our work a little easier. And we're given this function f of xy as x plus y minus x times y. Now, to make our way through the problem, step one, we need to find the CPs, or the critical points of f. To do so, we differentiate f with partial with respect to x, partial with respect to y, set both of those equal to 0, solve for x and y, and we'll get that 1, 1 is a critical point. So 1, 1 is our critical point in this case. And then the value of f at 1, 1, we see below is just 1. Once we plug that back into the function itself, that's the function f of xy equals x plus y minus xy. Okay, proceeding from here, we do step 2. There was only one critical point, so that's all we need to do for step 1. Step 2, we need to find the extreme values on D. There are some ways to do this that are easier than others. Parametrizing this with respect to a variable t, especially forming the line segments that form the sides of this triangle, so line segments, and using the formula that we were given back in chapter 10 to do so. The t range between 0 and 1, and the point between, or the line segment between each of these pairs of points are all formed below. R1, R2, and R3 are the 3 line segments that make up this triangle. This is the formula when we initially plug the points in, and this is our simplification to get an expression for each of those line segments, R1, R2, R3 respectively. Okay, we do this because we're going to need to find the maximum value of the function f of xy along one of these lines. Recall that this is an x component of this line. The first component is an x component, so that'll stand in place of x. And then this is a y component, so this will stand in place of y, the second component, and our function f of xy when we plug this in. We'll see the utility of writing this as a parameterized line segment shortly. Now, on R1, we need to find the maximum value of f on the line segment R1. So f of xy is the function we started with from above, and we can plug in for the line segment R1, our x component is 2t, and our y component is 2 minus t, the second component of that. So everywhere there's an x, we'll put 2t. Everywhere there's a y, we'll put 2 minus 2t. And that's what we have below. X plus y minus x times y. And completing that, we find that we'll rename this function g1 of t. And g1 of t is this quadratic function down at the bottom, or second from the last line. From there, we take the derivative of g1 with respect to t, and that's a simple power rule, and we just get 8t minus 4. We set that equal to 0. After doing so, we solve for t in that linear equation, and we get that t is equal to 1/2. So this is our critical point of the function g1 on this line segment. G1 is essentially, it's tracking the value of f, but parameterized for t. So we'll throw that on the list. Since it is a closed line segment, we want to check either end of that line segment. So the point 2, 0, and 0, 2 is also a reasonable place to check for the function f. But we can do the same thing by plugging in t equals 0 or t equals 1 to get to either end of that line segment. So that's what we'll do. We'll use 0 and 1 because that'll be consistent for all of these points, an easier way to check. So we've got a few layers here thanks to the parameterization, but if we're nice and organized, this comes out just fine. This is a longer way of doing it than what the book has suggested, but it is it's more fail-safe once you understand what you're doing. The book has the student reason through more of where these extreme values might occur. So for g1 of t, parameterizing f along that first line segment, R1, we have a critical point of t equals 1/2. The value of g there is 1, and that'll also match the value of f of xy, thanks to the way g has been defined. At the extreme points, 0 and 1, we get values of 2. So our extreme values from g1, the smallest is a 1, and the largest is a 2. So we'll track those off to the side. We're essentially done with that line segment. Okay, the line segment R1, we found the maximum values of f. They match this function g because g was defined in terms of f, just as a single variable parameterization. And we'll do the same thing for g2. Now we look at R2. That's our line segment, the equation of our line segment between the next pair of points. And we write down f of xt comma y of t. And this is our original function f of xy. And when we write in 0 for x and this 4t minus 2 for y, we have this expression here. And that comes out to the linear expression 4t minus 2. We set that equal to 0. And we get 4 equals 0. And then we conclude that G2 has no critical points. There are no solutions to that equation. So no critical points for G2. So we only check its extreme points. So either end of it, 0 to 1 is what this line ranges on. That's the case for each of these. So remember, this is t is between 0 and 1. So we need to check it at the endpoints, just like the closed interval test would tell us to do. And in this case, we've got a -2 and a +2. So the extreme values of G2 are -2 and +2. And again, extreme values of G2 represent possible candidates for extreme values of F on these boundary regions. Now that's R2. The third line segment, R3, we repeat the process. We recall what R3 is. It's X component here. It's Y component in the second component. And we form the function G3 of t. And we'll do the same thing. We'll find the extrema of G3 of t. Well, G3 of t is f of the first and second components with these parameterizations. G3 comes out to this quadratic. Take the derivative, set it equal to 0. Our critical point is t equals 1. That happens to coincide with also our endpoints of this line segment for t equals 0 and t equals 1. So there's no need to add another 1 to the line because g3 of 1 will be the same either way. And we get a positive 2 from there. g3 of 0 for the other endpoint of the line segment is negative 2. And we list the extreme values of g3 off to the right as well. And we've got negative 2, comma 2 again. Okay, so some of these points overlap, of course, because R1, R2, and R3 are connecting line segments between points that these line segments have in common. So a table to kind of put it all together and make sure we're not missing any and we're not double counting any or anything like that will be very useful. So we go through and summarize all the values we got out of this. Any of the extreme values for any of the functions g, g1 through g3, we'll list off in this column here. And in fact, the first column that was filled out was this column to say what value each of these functions, f or g, is output by this, because we can go back and trace information like what xy value occurs when t is equal to 1/2. But if 1 isn't a minimum here, then there's no reason, or maximum, then there's no reason to go chasing after what its xy value is, because it doesn't have any bearing on what we're actually looking for. So we list this first, and then we can pick out on the side what's a max and what's a min. Okay, if there are any ties, well then we certainly count each one and make sure they're either representing the same point. If not, then we add another point to where another maximum might occur. So anywhere there's been a max, I've gone back and I've tried to find the xy coordinates that were involved. Okay, so before finding the xy coordinates, to clarify that process, g1 of 0 was 2, and 2 seems to be the maximum global value of f or g, again, they're the same values, and that occurs at 0 and at 1 for g1. So when t equals 0, t equals 1, we plug that into R1, and the point we get out is 0, 2, and 2, 0. Okay, so these 2 points return from f a value of 2. Okay, we do the same thing down the rest of the table. The next one is a minimum. At g2 of 0, our output was negative 2. Remember, that'll match f's output as well from the way this has been built. If that's the case, we know that 0 is the t value we're interested in. So t equals 0 is what we place over here. We recall that R2 is our map from t to xy. And when we plug in t equals 0 to R2, we get the point 0, negative 2. I encourage the reader to do that. Plug in 0 to R2 and see that you get a coordinate 0, negative 2 for your xy value. And that represents the location of a minimum for f of xy. Working our way down the rest of the table, doing the same, we're able to identify which points, which t values correspond to which points, all the way through to the bottom here. And now we can throw out any overlap. Of course, we see that 2, 0 yields a maximum of 2. Well, it did the same here, 2, 0 with a maximum of 2. We only need to list that once. We see that 0, negative 2 shows up twice, yielding a minimum value of negative 2. Of course, we only need to list that once. So we just cut out the redundancies, but the table certainly helps us not miss any points where we double a maximum, right? We have 0, 2 yields a max of 2. We also have 2, 0 yields a max of 2. So that's a situation where we got a new one that tied for global maximum or absolute maximum. So such a table is always helpful in a problem like this. The overall results are listed below. Function f has absolute maxima, has plural maxima, 2 at the points 0, 2, and 2, 0. And then it has a global minimum, just a singular minimum, negative 2 at the point 0, negative 2. It's all based on this table. The table should be somewhat similar to what you did in Calc 1 as well with the closed interval test, only now with this in-between function g that helps to map from t to our function outputs, our f function outputs. So that is our closed bounded set optimization. Let's see an application problem. So in this example, we're asked to find the points on the cone z squared equals x squared plus y squared that are closest to the point 4, 2, 0. So the points on this cone which are closest to the point 4, 2, 0. Okay, well, if we're trying to find points that are close, that are on a given surface and closest to some other point, the best thing we can use is the distance formula. And we're looking to minimize the distance between 4, 2, and 0, 4, 2, and 0, and an arbitrary point x, y, z, which happens to be on the cone z squared equals x squared plus y squared. So the way we've set this up is we've got our distance between an xyz point on the cone and our point 4, 2, 0, and we want to minimize this function d, this distance function. There's a nice trick to this. You've probably seen it in Calc 1, minimizing similar problems. Since g of d equals square root of d, in other words, since the square root function is an increasing function, we don't need to minimize the whole square root of this expression, right? We can simply minimize d, or d squared, right? So the trick is to minimize d because its minimal points occur at the same points or point as the minimum of d squared. Okay, so in other words, we can use d with the radical expression up here, this, and try to minimize that with partial derivatives setting things equal to 0, or we can find the same minimal points by minimizing d squared itself. We'll call this function d squared f of xy once we get a substitution and get rid of that z squared on the end. But again, we don't have to minimize this expression. We can just minimize its square because the square root function will translate the minimum correctly from one curve to the other. So in other words, this function has minimum in exactly the same place where this function has minimum, and vice versa. Now, the minimization process on itself is just a matter of writing d squared down and then using a substitution for z squared on the right end of it, and that's x squared plus y squared. This is now a function of f, or function f of x and y, so we're ready to optimize it or find its minimal values. And doing so, we take the partial with respect to x to get this expression, partial with respect to y to get this expression, set them both equal to 0. Solve for x, solve for y. We've got x equals 2, y equals 1. Then use the constraint, the fact that the point needs to be on this cone. We plug in 2 for x, 1 for y. 2 squared plus 1 squared is 5. Z squared equals 5. So z is equal to plus or minus the square root of 5. That leaves us right here. Now, putting all this together, it's just a quick little finish to it all. The points on z squared equals x squared plus y squared, this cone, which are closest to 4, 2, 0, are both the points 2, 1, root 5 and 2, 1, negative root 5. So we have 2 points that are closest to that cone. The way we might think about that is to recall what a cone looks like in three-dimensional space. This cone is possibly elliptical on these ends or whatever, and 4, 2, 0 might have been a point right here, and then the closest point on the cone to this point would have been one here and one here, right? They might be well matched, something like that. It should probably look more perpendicular than the way I've drawn this point 4, 2, 0 down here, but I think you get the idea of what's going on there. That's why we have 2 points geometrically when we think about this. Okay, so that's it for section 11.7. There are some other applied problems, including volume of an open top box, which should look a lot like Calc 1 problems. But most of them are pretty straightforward, using formulas that are well known in this process for minimizing or maximizing a function of 2 variables.